Hello, programming languages students. Welcome back. By popular request, I am creating this video to cover to extend video 9 on recursion and talk a little bit about the dangers of um, and walk through this example of putting our recursive call first rather than second when you're designing your predicates here. And so we're going to start with a really simple example. I guess we're going to stick with a really simple example, which is we're going to start at the end of our tree and we're going to find out who descends from Donna. So we're going to descend Donna, comma, y, and we'll see what Prolog gives us. So before I run this, we can tell really quickly we're going to get one true answer very quickly. We're going to do descend x, comma, y, where x is Donna and y is a variable, the thing we're looking for. And this is true if we can find a child of Donna, and then we can unify that y variable, right? So we know that we're going to find child of Donna because Donna is unified with x, which means we're going to find child of Donna. And this is going to be a variable y, which we're going to be able to report back as a descendant. And so we're going to very quickly find that child of Donna is Emily. And therefore we can descend, we have a descendant of Donna's is Emily. So let's run that real quick. Now, we have a next here because there's still more predicates to search, right? We haven't searched this second descend predicate yet. So maybe there are more descendants of Donna. We don't know. And so when we run this, this is where we get stuck in our infinite loop. So the problem here, as you'll see reported pretty quickly, is that we have a stack limit exceeded. This is basically an infinite loop. And so what happens is we dive in to this descend predicate. And so we're checking descend Donna, comma, y, if descend z, comma, y, and child x, comma, or I guess x is Donna. We've already unified that. And then z. So this z will ultimately unify with this z. This y will ultimately unify with this y, but right now they're all variables. So basically we're saying who are the middle pieces here? If we're going to search further down the tree, what other descendants could Donna have? So the way this is ordered, the first thing that Prolog is going to have to evaluate is this descend z, comma, y. So we're trying to find a descendant of anyone. So any z, any y. What are my possible descendants? So we're going to try all the different combinations of children. None of them are going to yield a true result when we bring them back up and check up here, because there are no other descendants of Donna. So we're going to see if there are various combinations of people that are further down the list of children here. If there's various other pairs of children that, like, for example, if Emily had a child, that we could find and match and work our way back up. And so we're going to try all the possible combinations, and none of them are going to work. But because descend is first, that means that we're actually going to have we're going to infinitely call descend before, even if we run out of all the child combinations, we still could potentially have descend combinations, because when we try a descend combination, um, this is going to eventually run out of options and we're going to get falses here. But here we're going to recursively descend. So rather than actually walking through all the potential, all the options and all the details and all the depth here, I think the most important takeaway is this. You should always put the non-recursive predicate before the recursive predicate, or the recursive rule. So the reason for this, the principle, is that we want Prolog to evaluate the non-recursive goal first, so that if it runs out of options for this, if we do not have any possible children that would satisfy this, then we can really quickly stop searching. So once if we're searching all the child options first here, then as soon as we run out of child options to search, there is no potential calls. There are no more potential calls to descend. because, well, there's no more possible options here. If descend is first, then Prolog is going to try all the possible options of descend, and since it's recursively calling itself first, there's no flag to it to stop recursively calling itself. If it runs into child first, it stops. This is like short circuiting in Java. If you have an if statement, um, let's say if x is greater than 3 and x is less than 17. Well, you may not actually know this, but it's true. In Java, if the value of x were -5, well, we have an and condition here, and x is not greater than 3. So in Java, the question, the check for x less than 17 is never going to happen. It's the same idea in Prolog. It's short-circuiting. If we run out of child predicates and there's no possible child predicate that could make this descend true, then we're going to stop. And we're not going to actually evaluate descend z comma y. If it's the other way, then we're going to evaluate descend z comma y first. So for example, in this example, I guess this is kind of where the example breaks down a little bit, but if we had an x value that was 100, both of these are going to have to be checked. 100 is greater than 3, so then we have to make the second check. And so both happen. As it turns out in Prolog, though, it's the recursive call that's the only dangerous one. So it's almost as if this call, we want this call to be the dangerous one that could recursively loop and check things, and this call to be the easy one, so that if we can easily remove something from consideration, we never do the more dangerous recursive call. Hopefully that makes some sense. This comparison doesn't work exactly because these are both the same level of risk or the same type of call in Java. But in general, in Prolog, you want to avoid putting recursive calls first. You generally want to put recursive calls at the end so that you can short circuit your way out of them. So the difference between this example is that we have one dangerous call and one safe call. You want the dangerous call at the end so you can short circuit your way out of it more often. So that's probably more important than knowing the details about how the infinite descend tree works. Note that just to prove that this works, if I run with descend at the end, we find our first Emily here. We then check our descend predicate where we've try to find all the potential children that could work and therefore check if they are descendants. So we're going to do some of this. But once we run out of all the child options, child pairs, then this will evaluate to be false because no child pairs were found that worked, and we've evaluated all the different child pairs. So therefore, this gets short-circuited out, and we no longer actually check the recursive call, which leads us away from getting into an infinite loop. So again, the most important part to this isn't necessarily diving deep in there, but the real takeaway is put your recursive calls at the end. So if you've evaluated other possible subgoals that work, you recursively call. But if you have not, then you short circuit your way out. Hopefully that makes sense. It really probably is not worth really diving into the really specific details about how this ends up working, but the important part is just that short circuit. So please let me know if you have other questions. Thanks.